Welcome everybody. In this video and series, we'll be covering the building blocks of financial mathematics. In these videos, I will cover everything you need to know in a summarized fashion. I will show you examples and I'll show you all the formulae that you need to know. I will also give you exam tips. This series is great if you're just starting with the content or if you are revising. I have split section 1 into 3 small parts. These cover the foundations of the course and we will build upon these in later sections. So why is financial math so important? Well, we use it to place a value on money over time, and this we call the time value of money. This is because much of the activity in the world of finance and investments involves the buying or selling of assets or businesses, and these assets or businesses can be viewed as a series of cash flows. These cash flows are paid over time. Positive cash flows are the ones that you receive, while negative cash flows are the ones that you pay out. And we are interested in putting a value on these future cash flows today. The concept of interest forms the center of financial mathematics. And interest here is the cost of using money that is not yours. It could also be viewed as what the borrower pays the lender for use of that money. There is an opportunity cost to holding money instead of investing it, and the extent of this opportunity cost will depend on the amount of interest or return that can be received from investing the money. In this section, we start off with part 1, where we understand the difference between simple and compound interest. We then move on to part 2, where we break down and unpack the concept of the time value of money. And we end off with part 3, where we learn how to move between nominal and effective interest rates. The difference between simple and compound interest is the way you apply the interest. So we can use the same interest rate in each, but we apply them differently. Let's use an example of an effective interest rate of 10% per annum, which we denote with the letter I. Per annum is Latin for per year, and it's often abbreviated as PA. So our time period for our interest rate is a year or yearly. Under simple interest, only the principal earns interest. After that, any interest earned does not earn any more interest. The principal is essentially just a sum of money. It's usually what we have at the start of our period. Let's look at an example. Let's use a principal of $100 and call it C, and an interest rate of 10% per annum. Let's call this I. Now let's draw a timeline showing 3 years with our principal of $100 at time 0, which is now. Then after 1 year, we still have our principal plus the interest that we earned. This is 10% of $100, giving us 10. So in total, we have $110. Now we can rewrite this in our notation in terms of our principal and interest rate. At the end of the second year, or after 2 years, we have our $110 from the end of year 1 plus interest. Because we are using simple interest, only the principal from the end of year 1 earns interest. Again, we can rewrite this in terms of our notation and we can simplify it. We do the same for year 3 and we start to see a general pattern in the notation. This leads us to the general formula. More formally, this formula gives us the accumulation of a principal of C invested over n years at a simple rate of I. Note that our period under n, our term or our period, matches our interest rate. In other words, they are both yearly. So this formula tells us that if we start off with a principal of C at time 0 and nothing is added to the principal, you will have C times 1 plus Ni after n years by applying a simple rate of I. Now when we apply a compound interest, rate or compound interest, both the principal and the interest continues to earn interest. So we don't have to split them up anymore. Let's use an example using the same assumptions as before. We start off with our timeline, and for the first year, we will note that the calculation is the same as under simple interest because we only have the principal to consider. This shows us that the interest earned is $10, giving us a total of $110. We can write this in our general notation and we will find that it's the same as under simple interest for the first year. Now in the second year, or after 2 years, we have what we ended off with after year 1, which is $110. Now since this is made up of both the principal and interest, and since under compound interest they both continue to earn interest, we don't have to split them up. And we apply the interest rate to the full amount, giving us an interest amount of $11 and a total of $121. Again, we can show this using general notation. Now let's expand this fully. We can start off by taking out C as a common factor, and we can then multiply right through. At this point we will then factorize and we can get the following. Bringing this in, we can see that we have C1 plus I squared. Doing the same for year 3, we get to the following general notation. And this leads us to the following general formula. More formally, this formula gives us the accumulation of a principal of C invested over n years at a compound rate of I. Again, note that our period under our interest rate matches the period of our term. And the idea of the interest rate continuing to earn interest leads us to the compounding effect. Einstein has the following famous quote, which in the next slide you will understand what he meant. We have two graphs here. Both show a principal of $100 earning 8% per annum under both simple and compound interest. The first graph is over a period of 9 years. What you can see is they grow fairly close in the beginning, but towards the end they start to diverge. You end up with 2 times what you started with under compound interest and a bit less under simple. Over a longer period of 35 years, the compounding effect really shows. You end up with 15 times more compared to a lot less under simple interest. 35 years is about the working lifetime of the average person, and this concept shows that if you start saving early, you can benefit from the compounding effect and compounding returns. And this is particularly useful if you are saving for your retirement at or after age 55. For key takeaways, under simple interest, only the principal earns interest, and this is the formula we use to accumulate our principal. In other words, if we want to know how much we will have after n years, starting off with the principal of C. Under compound interest, both the principal and any interest earned will continue to earn interest. We are generally using compound interest rates, so unless it states in the question that the rate is a simple rate or that simple interest applies, you can usually assume that compound interest will apply. Always make sure that your interest rate period matches your period in the question or end. So notation is always important when answering a question in a test or an exam. So for example, if I'm using 2 or more interest rates in the same question, I want to be sure to label them clearly. I could use I1 for the first one and I2 for the second one using a subscript, or if I want, I can just call them I, J, and K. That way the examiner or the marker can clearly understand what I am using, and this is very important, especially in later sections. You have made it to the end of part 1. If you like this video, please add a comment and share it with others. Please continue and check out part 2.